Let f denote a field. Let m and n be positive integers. For each I from 1 up to m and each j from 1 up to n, I have an element from the field f aij. And for each I from 1 up to m, I have an element from the field f bi. A system of linear equations in the variables x1 to xn defined over the field f is as follows. So we have m linear equations that have to be simultaneously satisfied. And to solve a system of equations that look like this is to find values from f to assign to x1 up to xn so that the left-hand sides are equal to the right-hand sides. System of equations can be defined over structures other than fields, but we won't look at them here. And very often, the field f is the set of real numbers, the rational numbers, or the complex numbers. Here is a system of two linear equations in two variables, and we are defining it over the real numbers. And the solution is given by x1 equals minus 1 and x2 equals 1. You can easily check that. If we substitute x1 equals minus 1 and x2 equals 1 to the first equation here, I get minus 1 plus 3 times 1, that's 2. And if I substitute these into the second equation, I get minus 1, which is positive 1, plus 2 times 1, and that is 3. Being able to solve system of linear equations is actually very important. There are many applications that rely on that. For example, weather forecast, portfolio optimization, etc. What we're going to do now is to look at two very special cases. The first case that we are going to look at is when the system has only one variable. And let's look at the following example defined over the rational numbers. And I'm going to label these equations 1, 2, 3. So the question is, can you find a rational number that you can assign to x that satisfy all three equations? Now, equation 1 is equivalent to the following. If you multiply both sides by 1/2, you get x equals 4. And equation 3 is equivalent to the following. If you multiply both sides by 1/3, you get x equals 2/3. So x has to equal to 4 and 2/3 at the same time, which is impossible. And so this system has no solution. In general, if you have a system with only one variable, what you need to do to solve it is to first convert every equation into this form, x equal to some constant beta. Now, if every equation converts to the same form with the same right-hand side beta, then beta is the solution. Otherwise, there's no solution, as in this example here. So this case is not so difficult. The second case that we're going to consider is when there is only one single equation, but we can have more than one variable. We'll look at an example over the rational numbers. Say this is the equation that we want to solve. In other words, we have to find rational numbers for x1, x2, and x3 that satisfy this equation. Now, what I'm going to do is, I'm going to add minus 2x2 plus x3 to both sides of the equation. And if I do that, the left-hand side is going to be left with just x1, and the right-hand side will be 5 minus 2x2 plus x3. It's clear that no matter what values of x1, x2, and x3 we assign down here to satisfy this equation, those values will satisfy this equation, and vice versa. If you look at this equation here, what this is saying is, once you have picked values for x2 and x3, you just have to set x1 to 5 minus 2x2 plus x3. And there's no constraint we need to impose on x2 and x3, so x2 and x3 can be anything. For example, setting x2 equal to 0 and x3 equal to 1 gives x1 equal to 6. And so a solution is given by x1, x2, x3 equals 6, 0, 1. But we can set x2 to an arbitrary rational number, and the same thing for x3. So let's set x2 to some s, and x3 to some t, where s and t are rational numbers. We get that x1 has to be 5 minus 2s plus t. And so x1, x2, x3 equals 5 minus 2s plus t, s, t, is a solution for all choices of s and t. So in this case, there are actually infinitely many solutions. And more generally, a system of linear equations with only one equation, but at least two variables having non-zero coefficients, has infinitely many solutions, unless the field has only finitely many elements. Now that we have taken care of two special cases, we'll see how we can solve systems of linear equations of any size.